The second talk. This one is going to be by Sergei Kharitontcev Beglov on LLMs and program analysis.
Hi everyone, I'm Sergei Kharitontcev Beglov, and now I'll tell you about my project. My current project, it's called correctness via program analysis. This is also my bachelor thesis in Kazakhstan University. So, language models, like the ones we use today, are very great at handling text and code, but there is a big challenge for them. They often generate incorrect code. For this example, I asked to generate an implementation of a grid algorithm in Kotlin. So this implementation has a bug. Could you probably find it? So while we're looking for it, I can tell you that right now the only way to check if generated code is correct is by manually checking it by person. And now programmers tend to use AI assistant more and more. So as AI assistant become more popular, a lot of bugs could appear in the code bases. So the bug here in the worst condition, there definitely should be num2. And yeah, it's easy, straightforward to find the error here. But in the larger code bases, this could be more difficult because of size and complexity. Several papers already pointed at this topic, but our approach tries to reduce reliance on the LLMs in the implementation of correctness tools, since LLMs could hallucinate or be wrong while calculating the correctness. So the current methods to improve code generation is stated here. So the simplest one is to modify prompt. For example, we can ask a more polite, or offer it cheap, or just threaten it, and so on. Moreover, we can add some additional rules, create some code constructions, so to escape some tricky violation of the rules. This part I named prompt engineering. A second technique is known as chain of thought. This technique was introduced by Wang in 2022. And for example, for prompt, I have 2 apples, and I bought 3 apples. How many apples do I have? We just add an example. If I had 1 apple and bought 2 apples, I will have 1 plus 2 apples. That equals 3 apples. So this type of prompt is called chain of thought and increases the correctness of answers a lot. Also, we can modify the prompt with adding some additional context. For example, some additional source files or some project structure to improve the understanding of the code base. So this method is called context injections, but this technique need to be adjusted because LLMs in the current state have very, very small context to be used. So this is a difficult task too, and it's not auto. And other techniques using different models, we can use a lot of some bunch of models and compare solution by different models to choose the best one or consistent. Also, we can fine-tune the model to better understand the chosen language or the chosen code base, like project, a big project like Ontology IDEA. And we can use program analysis. The simple techniques that use program analyzing is just using compilers or static analyzers as a feedback loop. We can generate code, check for errors, like compile or lint the code and give it as feedback for LLM to carry the code. That techniques is used by my work. I try to generate several solutions and generate tests for each solution. Running tests on the whole solution, I will find the most consistent one that generated a lot of times, and so on. So consistent. You can see an example. I asked a model twice with the same prompt, and the model returned two different answers. Answers differ not only by variable naming, but the internal implementation. The first implementation uses model operation, and the other one uses subtraction. So yeah, we came up with some hypotheses. So if language model generates the same many times, is that solution, generated solution, correct? Anyway, so some solution. So what means the same? So basically the same could be mean the same source code. So comparing source code like text files is very common task in natural language processing. There are a lot of techniques, metrics, and so on. And moreover, it's very easy to compute some metrics of similarity. But we have, as I show later, we have some problems with formatting, some code changes. For example, Kotlin is not empty and is empty functions. And yeah, of course, variable renaming could lead to invalidation. But on the other hand, we have equality based on behavior. And we need to somehow compare behavior on all possible inputs of the program. But as computer science states, it's an undecidable task because firstly, we need to understand if the program stops. But we can come up with some approximation. So yeah, that will be easy to compute. Yes, and it can be altered with non-semantic code changes, with something like this, and yeah. So yeah, let's talk about the syntax metric. So the first metric that we used was some simple chart-to-chart comparison. We can see like the reference and two solutions. One to 0 because two programs are not equal. And the second pair, like the first and the third solution, are equal. So the technique is very easy to implement, but it has several drawbacks. For example, the first one, the most major one, that it's binary. Solution are equal or not. If you want to find some correlation between semantics and syntactic metric, or we just want to see any smooth metrics of how solutions are similar, we need something more smooth. Moreover, it's not robust to white spaces because sometimes large models generate solutions that differ with just semantic. For example, using 4 white spaces instead of 2, or just using new lines or comments. Moreover, language models are easy to rename variables across solutions. For example, we generate 2 solutions, and the first one will be will have just good variable namings that will be understandable, and the second one will have just one letter named variables. So yeah, this lead to invalid result. And yeah, as I said earlier, this matrix can't understand syntax sugar. Like, for example, we have in Kotlin is empty, is not empty functions. In Java and C++, we have implicit type signature. For example, out of keyword or by keyword in Java, and so on. So also our second implementation uses charF. It's metric that came from large world of natural language processing. And the first question, why have we chose this metric? So our colleagues from ML4 laboratory have wrote a paper about what automatic metrics are the best for you for program similarity tasks. So in the paper, they came to conclusion that charF is the best and in the task of behave as a human. So we have choose this metric. So how this metric works? Basically, this metric is F2 score of based on n-grams. That means that we have n-grams. It's just n adjacent symbols in the string. For the string dem, it will be dem m and m. And yes, after we calculate precision, just number of n-grams that are in the reference. There's a question just, can we use embeddings vectors for comparison? Yes, I will talk in the next slide. Char just uses is used in the task of comparing the hypothesis to a reference. So they have the hypothesis and the reference. So precision is just a percentages of n-gram that are in the hypothesis and present in the reference. And recall is just percentage of n-grams that are present in the reference and also in the hypothesis. So what advantages of this metric? First of all, this metric is very robust to formatting. So it excludes any white space, tabs, and new lines. Moreover, using of n-grams helps to smooth some difference in variable naming, and that is the best. Some syntax sugar like is empty or is not empty.
Why do you say that it's not affecting the metric a lot formatting?
Sorry?
Does it? You say that formatting such as white spaces and tabs could not affect the metric a lot.
At all. Sorry, at all.
Okay.
Because implementation of charF that we use just removes all white space samples. Okay, yeah. So yeah, there was a question in the chat about vector embeddings. So after we implemented charF, a paper about code-based code just came out, and we wanted to look how it looks in our experiments. So basically, code-BERT is a metric based on BERT score. BERT score is this metric that encodes to text the hypothesis and the reference using BERT model and compare embeddings using cosine similarity score. So yeah, this metrics should be better, but in our case it was not suitable because we trying to compare generated code, and in our case we want to distinguish some solution in categories, but this metric it run just a big cloud of solutions. So despite of charF, so we can just use it for now, but we consider using it later. Yeah. So yeah, one more example. Example of the task. This task of merging two linked lists. So linked lists. So the first implementation uses just cycle and uses recursion, and the second one uses the cycle. So we clearly can see that they implement the same task, but this metric is low. Sharef has a range from 0 to 1, so 0.41 is a bit low. So our solution just came to the hypothesis that the solutions are not equal. So we can talk about the semantic metric. So to use in semantic metric, we use the thing named differential testing. So what have we done? We generate. So we generate tests, and we generate tests, or we will generate tests before the running solution, because some data sets gives access to the test for each task. But so the solution of using manual test, where you generate tests and compares output of the reference solution with our solution. But our task uses test generation, where we generate tests automatically via our tools and compares output of solutions. For differential testing, we're using to develop in our model, right? KEX. So the solution utilizes method of concurrent testing. And what we done, we just using concurrent testing with tester function, we call the result of two functions, left and right, and I saw that they are equal. Why have we done this? Because KEX couldn't assess the logic. It only traces that by running the program, no exception was thrown. So we need somehow for exception on the function loss. So to calculate our metric, we're using pairwise comparison. We compare all solution pairwise, and after it we can collect class of equivalence. If some group of solutions are equal pairwise, so we can say that this one class of equivalence, and after it we can split all edges into 3 categories. Component edge, it's an edge inside the component. Border edge, it's an edge not stated here, it's edge between 2 components, for example, this one. And outer edge, this edge that has no components on the edges, because I stated that if only one solution in the class, it's not a class, it's just one solution. So there is some kind of outer edges. So these components use it to, for example, choosing the best class with the best solution. So if you need to if you want to benchmark our metric, we need to choose the best possible solution. So the best solution is some solution from the biggest class of equivalence. So if you have a class consists of 3 solutions out of 5, we say that it's the best component, and we can benchmark it against some reference solution if our data set has a reference solution. So let's talk about data sets, because it's the most important part for running experiments. The first use data set is just a lit code. Lit code basically is a set of logarithmic problems divided by difficulty level. Each task has some description, stated in English, some examples, and input-output constraints. So we've chosen 170 easy and painful tasks. In the picture, you can see an example of a medium task. And the second data set that we used was human eval X, because we needed a data set with reference solutions. Human eval X is a data set for Java. Yes, and the tasks are just comparing some stated code. For example, it's just function declarations and comments what the function should do. And this set contains 164 problems. Yeah, but that set has a lot of problems. The first one, that reference solution not always correct. I have corrected some solution because it was incorrect. Moreover, the task in the set are very easy and usually solvable in 10 to 25 lines of code. And yes, 150 plus solution tasks is low because during our experiments, number of passing solution to the next stage always decrease. So yeah, let's talk about experiments. So for experiments, I set up this pipeline. From the dataset, we generate solution using Grace APIs that utilize some OpenISA models. After that, they pass to preprocessors that somehow prepare solution, filter it, and so on. After that, it's goes to the processors that calculates metric, syntactic, or semantic real pairwise computing. And after it's going to post processor that usually some reports maker, solution server, and so on. So our first experiment was a hypothesis confirmation. So if we generate the same solution multiple times, is it correct? So what have we done? We calculated semantic metrics and choose the best solution for each task and tested it against the benchmark using the semantic metric maximum. So the results are clearly seen. There is a correlation. More expression correlation, you can see that its value like 0.9, but any our experience with syntax metrics was unsuccessful. There are no correlation, and as you can see, not all solutions came to the benchmark part because only the time solution with semantic score passed to the next stage.
Okay, sorry. Could you please explain the graphs a bit more?
Yeah. So this plots the relation between semantic metrics on the XX and benchmark score is semantic metric of the best solution and the reference solution. This is the same, but we use lexical score instead of semantic score. And on this plot is just distribution of semantic score. So it's just number of solution in each bin.
Thanks.
So yeah, the second experiment was about number definition because for each experiment, so as number of iteration increases, the number to compute the scores increase too. So we need to choose the best possible option and that give us the most numbers of consistent solution to time compute. So as we can see, using only two solutions and computing consistency across two solutions is the best option because it gives the same number of consistent solution as n equals 3 that was used in the previous experiment. And it's just faster and uses less number of accesses of language model, so it's more cheap. Yeah. So the last experiment was about scalation, symmetric and semantic metrics, because if you want to implement client applications that are actually running in the ED, we need sorry, we need to make it responsive. It should run fast and use as less resources as possible, but it's couldn't be very good. It could be under approximation, so we can just throw away some results that actually true, but we just haven't found it in our approximation. On the other side, we can implement server-side applications that allows us to slow execute all that we need, all things that we need, like we can use semantic metrics as we have now, and we can use as much resource as we have. So our first attempt was to divide all edges to two categories that are within component and outside component. So yeah, as we can see on this plot, we have some distribution of edges, similarities of edges across classes. So as we can see that the classes are not distinguishable in either way. So we try to second attempt. So in this attempt, we tried to split solution into three classes that are definitely equivalent solutions, that type of solutions, definitely inequivalent solution, that type, and classified solution, all other solutions. So to do this, we just use it to thresholds, green and red lines. And yeah, so the results that we have split 20% of solutions as definitely equivalent or inequivalent solutions, and 60% of the solutions were true split, so it was true results. So that are very bad. So in the summary, yeah, for GVM languages that we used, 92% of solutions were generated correctly, and 72% of solutions was compiled successfully. That are not bad metrics for language models, but only 37% were consistent. And it's maybe our problem because our implementation already has bugs, and we have some problem. I have some problems with prompt because some solution generates for different versions of Java and not always comparable. Yeah.
Sorry, could you please show?
Yeah.
Like, I'm a bit confused. What does it mean for solutions to be generated correct?
Yeah. So yeah, in some data sets, I need some structured outputs like JSON-like format because I need to find entry point of the solution, and I need to. I'm just asking LLM to generate JSON with entry function and the code, and in some station it just generates incorrect output.
So this 8% just something which is syntactically wrong for the output you expect.
Yeah.
Okay, I see.
So yeah, as I said, for Human we have just a small amount of data, and it's not very good. But on the other hand, we have more easy things to analyze because we have static timing and our language are compilable. Moreover, we have some known tools for text generation, and we have some knowledge about compiler APIs, so it's easy to us to write solution for GVM languages. But like the sets tend us to implement quite some implementation of semantic metric. So now I'm adding Python semantic metrics because our colleagues from MLFS here lab implementing low-code RM dataset that has more difficult tasks and just bigger. So for this, I used Penguin text generator. It's mutation text generated, made possible the state-of-the-art technology for now in Python community. And it supports the modern Python, so it's good because we have some problems with the Java version in the datasets earlier. So for now we will have not any troubles with it. But we face that low quality of tests. Mainly it's because Penguin generates for only one function, so we can so it's ignoring coverage for other functions, and our implementation of these functions are just framework as well as it was, and moreover it's ignores type. So because of dynamic typing in Python, we have some problems with it. So yeah, our future plans is just add reference solution to the red code and benchmark against it, and add Python in the semantic method. Moreover, we need to continue testing our hypothesis of syntax semantic relation, so to implement our findings into the assistant. And one other possibility that came not a long time ago is to use our platform, our line, to compare multiple text generations using LLMs or existing external solutions and so on. In case of LLM. So that's all. Thank you.
Yeah. Could you please go back the slide? So about this fully add Python in the semantics metric. What do you mean by?
We need to improve first. We need to improve some. We need to improve the quality of the test because now we have pure tests that always say that semantic metrics for Python is one in a lot of cases, and then managed checked solutions that are not semantically correct, like not semantically equal. So there's just couldn't cover all possible inputs for easy problems like 2 ifs and var float cycle.
Mm-hmm.
I have another question. When you compare two different solutions, do you skip things which are not important, like names of private variables or private properties?
You're talking about status comparison. No, we just compare the in static metrics, we skip the common part, like if two solutions have the same declaration or the same inputs, we skip that part, but we compare only generated parts. So private variable names, private functions, all that will be compared.
So, and when you create code generation, do you set up the target platform, like different versions of Java when you feed data into it? Because you could have different versions. Java have different validity.
Yeah, I do, but I can do it for datasets because datasets has 17 solutions, reference solution for 17 Java, and our test generator is able to generate tests for 11 Java. So I target fetching data and all test generation for 11 Java. But yeah, we have some troubles with reference solutions.
So you mean you cannot identify to which Java version reference solutions belongs to?
No, it's we just have some compilation errors. So we can just use some reference solution and I need to manually fix it.
Good. Thank you.
Why you didn't use some structural metrics for comparison, like metrics based on comparison of ATL trees?
So yeah, as I said, yeah. So that question is answered in a paper by Kharitontcev, basically because that metrics are not so good. So, for example, they compare char against meteors that uses some IST basis analysis, and code blue that are basically blue metrics for code for AST. So they're just worse than char. And yeah, so this paper is a bit popular because of that conclusion that simple char is better than other metrics.
So if I got you right, the paper states that simply counting n-grams is actually a better solution than comparing the structured trees of the programs.
Yeah.
Wow. Well, okay, thank you.
How you can prove it, or how you got this?
You can read the paper that's stated in the bottom of the slide. That's not mine conclusions.
So you don't know if it's true or not?
No, of course I read the paper, but it's so the paper compare the metrics against the metric of following the human behavior of comparing two solutions. So the Sharef was the best one in that kind.
It's just like we want correct solution and maybe better solution. They not always should be the same. But if it's correct and for different situations, you could have, you don't want recursion. Maybe you want the cycle version of the same code because you don't have that limitation in the memory. It's much easier to handle memory without recursion.
Yeah, but it's not affected. Like for humans, the task for us to compare a solution, just say they are the same or not the same. Like they solve the same task. You clearly can say that that two code fragments solve the same task. Thank you. So yeah, and we need from our metrics that the ability to just say that, yeah, the solution solves the same task or not. And for example, the best metric you according to the Kharitontcev paper is Sharef. It's not able to do this in that case.
Okay. Did you consider it to generate like a happy path and unhappy path and corner case path as tests to validate if solution works on some amount of input data?
Basically, so a tool that we used, Kex, is trying to cover the all possible. Is trying to cover the program with all possible paths. So became possible just restrict X by timeout, and it could generate some corner cases and so on. So yeah, but we haven't tried it because we were not optimizing the runtime of semantic metrics. We were trying to utilize syntactic metrics.
Okay, thank you.